So let's continue then. So we want to prove that lambda times f, where lambda is greater than or equal to 0, is going to be Riemann integrable, and that the value of that integral is going to be lambda times the integral of f. And we're going to use this result here that holds true for lambda greater than or equal to 0, which we proved in the previous part, which says that if you have a set y which is constructed from the set x by taking a multiple of all of the elements, which are written like this, but of course formally this means take all the elements in the set x, multiply them by lambda, and that's going to make your set y, then the supremum of this set y is equal to lambda times the supremum of the set x, and the infimum of the set y is equal to lambda times the infimum of the set x. So let's see how we're going to use this. So we want to understand why this function lambda times f is going to be Riemann integrable. So it's going to be Riemann integrable by definition if the supremum over all dissections of the lower Riemann sums of the function lambda f is equal to the infimum over all dissections of the interval ab of the upper Riemann sums. Now, let's think about what the lower Riemann sums and the upper Riemann sums are going to be, because actually we can write them in terms of upper Riemann sums and lower Riemann sums of the original function f. So let's firstly start with the upper Riemann sums. We always start with the upper Riemann sums rather than the lower Riemann sums. So by definition, this is going to be, so firstly let's say our dissection D, it's a general dissection, it's cutting it into n pieces, that interval AB. So it will be the sum from I is equal to 1 to n of xi minus 1. Those are the lengths of all of the bits that the dissection is cutting the interval up into, and then times the supremum of the value of, and it's going to be lambda f, almost made a mistake there and wrote f, so it's going to be lambda of f of x, but of course that is just lambda times f of x, for x is an element of x I minus 1 to xi. Now, look at this supremum, look at this set. This is the set of all of these values, lambda times f of x, for x is an element of this set. Now what we can do is apply our supremum result here, because this set, if you look at this set, let's take our y is the set of lambda times f of x, where x is an element of this interval xi minus 1 to xi. Our set x, meanwhile, is the set of things f of x, where x is an element of that interval. So hopefully you appreciate that these two sets are connected in this way that we looked at previously, so we can apply these rules. So just to absolutely convince you of that, here for the set x, we go in this interval xi minus 1 to xi, we take every single element in that interval, every single real number in that interval, we plug it into f, we collect the value, we stick it into a set. Here we go over the exact same interval, and this time we just take all those values of f of x, but we multiply them this time by lambda. So truly, this one is going to contain all of the elements of this one, just multiplied by lambda, so they are related to one another in this way. So this supremum is the supremum of y, so this thing that I've written here, this is the same as the supremum of this set. That's really just what it means. This is just a nice, beautiful way of writing this. It's the supremum of this set. And therefore, this is just equal to lambda times the supremum of x by our result above. But then we could write the supremum of x in this sort of notation here. So this is just going to be lambda times the supremum of the value of f of x, where x is allowed to vary over that interval xi to xi minus 1 to xi. So we're just converting between notations here. This means this, and then it's equal to lambda times this, which then writing it back in this notation is this. So let's put this together. So our upper Riemann sum, therefore, we can pull that lambda out because it's going to be the case for every single one of these intervals. So for all I, they're all going to, this manipulation is going to apply. You're going to be able to pull out the lambda in this way. We didn't have to presume anything about this interval xi minus 1 to xi, so it's going to hold true for all of the little intervals that you've partitioned your overall interval into. So you're going to end up with a lambda there, so you can pull the lambda out the front. So it's going to be lambda times sum from I is equal to 1 to n of xi minus 1 times the supremum of the value of f of x, where x is allowed to vary over this interval xi minus 1 to xi. But of course, this is then just the definition of the upper Riemann sum of f over that dissection. So this is equal to, therefore, lambda times the upper Riemann sum over the dissection d of the function f. So there we have it, a beautiful result, that the upper Riemann sum over any dissection of the function lambda of f is just going to be equal to lambda times the upper Riemann sum over that dissection of the function f. And of course, the similar thing holds true for the lower Riemann sum. Let's write that out as well. So if we consider the lower Riemann sum over a dissection d of lambda times f, by definition this is this sum from I is equal to 1 to n of xi minus 1 times the infimum of the value of lambda of f of x, which is just lambda times f of x, for x is allowed to vary over that interval xi minus 1 to xi. But again, this set here that we've got is all these values of lambda times f of x, where x is allowed to vary over this. This is just lambda times the set of all the values of f of x, where x is allowed to vary over this. So now we can apply that rule that this is lambda times the infimum of that set x. So this is the sum from I is equal to 1 to n, and then we're pulling the lambda out, and we can pull it out to the front again, because it's going to be the case for every single one of these intervals that lambda is going to come out. So we'll have xi minus 1 times then the infimum of just the value of f of x now, for x is allowed to vary over the interval xi minus 1 to xi. But of course that's just the definition of the lower Riemann sum, so this is now lambda times the lower Riemann sum over the dissection d of f. So this is the definition of the lower Riemann sum for our function f over our dissection d. So those are two very beautiful results then. Let's bring them up here and put them here. So we have now, given any dissection d where we're partitioning the interval ab into n pieces, that the upper Riemann sum over that dissection for the function lambda f is equal to just lambda times the upper Riemann sum for the function f, and similarly for the lower Riemann sum of the function lambda times f, it's equal to lambda times the lower Riemann sum over that dissection of f. Well, now what we just do is we plug these things into this bit that we want. So remember, what we need to think about is what is the supremum of the set of all lower Riemann sums and what is the infimum of the set of all upper Riemann sums, and we're asking, are they equal to one another? That's what we want to be the case. For this function to be Riemann integrable, those two things need to equal one another. We're going to use this to show that they are, and then we'll find what the value is actually going to be equal to, and that will be the value of the integral of lambda f. So let's firstly think about the infimum over all dissections of the upper Riemann sums of lambda f. Well, now that's going to equal the infimum over all dissections, and we can now replace the upper Riemann sum of lambda f with lambda times the upper Riemann sum of f. So now again we can apply our infimum rule, because this is a great big set here. So our sets here, our set x is going to be the set of all upper Riemann sums of f over all dissections. So that's a hugely complicated set, and I acknowledge that because there are infinitely many dissections. There's unbelievably many dissections. But we can still imagine this concept of all the possible values of the upper Riemann sums here. And then our set y is going to be just multiply every single one of them by lambda. So you keep the same set. Oh, what am I doing here? No. So again, you go over every single possible dissection, you find all the values of the upper Riemann sums for our function f, and you just multiply them all by lambda. That will be the set y. That's what we're now trying to take the infimum of here. We're going over all dissections and we're trying to find the infimum of this great big set. So this is effectively the infimum of y. That's the infimum of this thing that I've written down as y. In fact, I can drop that over all dissections now. It's the infimum of that set y. And that value is going to be the same as the infimum over all dissections of the upper Riemann sums for my function lambda of f. So now what I can do is just apply my result. This is just equal to lambda times the infimum of the set x. But of course this, now let's write it back in other notation. This is equal to lambda times the infimum over all dissections of the upper Riemann sums of the function f. Brilliant. So that's very helpful. So we now know that the infimum over all dissections of the upper Riemann sums of lambda f is equal to just lambda times the infimum over all dissections of the upper Riemann sums of f. Now let's do the same for the supremum of the lower Riemann sums. So if we think about the supremum over all dissections of the lower Riemann sums of lambda f, again we can instantly replace that with supremum over all dissections of lambda times the lower Riemann sum of f. And now I won't go through it in quite as much detail as here, but we can just apply the same rule. We're going over all dissections here, creating this great big set of lower Riemann sum values, and then we're multiplying them by lambda and taking the supremum of that. Well, of course, it's just going to be equal to lambda times the supremum over all dissections of the lower Riemann sums of f. So this is equal to this. But now we know something. We know that the function f is Riemann integrable over the interval ab. That was our starting assumption. So that means that the supremum over all dissections of the lower Riemann sums of f is equal to the infimum over all dissections of the upper Riemann sums of f. That's just the definition of Riemann integration. And that that value is what we call the integral of f dx over the interval ab. So this is what we know from the fact that f is Riemann integrable. But now look what we've got here. So I think that shows everything that we need. We have that this one is equal to this, and this one is equal to this, but we know that these two things are equal to one another. So this, in fact, is just equal to this. So we can draw another equality, and I'm kind of running out of space to do this, but this thing is equal to this thing because of what we've got here. This is equal to this, so just multiplying them both by lambda, the equality still holds true. So this is equal to this, but then follow all the equal signs around, and you overall have got, therefore, that this is equal to this, which is exactly what we wanted to prove, that the supremum over all dissections of the lower Riemann sums of lambda f is equal to the infimum over all dissections of the upper Riemann sums of lambda of f. So yes, lambda of f is going to be Riemann integrable, and what is the value of these two things? Because that's going to be the value of the integral of lambda of f. So these things are equal to the integral from a to b of lambda f dx. And what are they equal to? Well, just follow some of these equal signs around. They're equal to this, but this thing here is equal to this. So this is equal to lambda times this. So we therefore have that this is equal to lambda times the integral from a to b of f dx. So that's the first little bit of linearity proven. In the next part, we'll go on to number 2.